Hello, my name is METİN ARIDAŞIR. This is 311th part of explanation of my theory. Yes, there are no electric force between electrons and nucleus in an atom. There are no attractive, repulsive electric forces between electrons and nucleus in an atom. How? Yes. Contrary to accepted physics theories, according to my theory and my formulas, 1. Electrons are not identical particles in a multielectron atom. Each ionization energy for instance 7 proton nitrogen or 7 electron nitrogen multielectron atom, first, second, third ground state ionization energies for each electron. Here, data. Electrons are not identical particles in a multielectron atom. Each ionization energy represents a different proton bound electron with different wavelength. Okay. Like what? Like this. Seventh ionization energy represent smallest electron motion form in a nitrogen atom, and its wavelength is 1.8582 nanometer. Then sixth ionization energy corresponds 552.0718, I'm so sorry, 2.2453 nanometer wavelength electron. Different wavelength electrons according to me. Okay. Here's largest electron represented by first ionization energy, and this is my formula for each spectral lines. And for instance, here NIST data, National Institute of Standards and Technology, nitrogen, left side my prediction, right side observation, experimental data from NIST. Here my computation according to this formula that I put forth, and here sixth ionization energy corresponding electron which 2.24, and here seventh ionization energy corresponding wavelength 1.885 X-ray 7 here. Okay, then here what is that? It is 21222. What represents? Represents ground state, first ionization energy, ground state, second ionization energy. Data from NIST, here data from ionization energy tables from Wikipedia. Look at that. According to this, okay, first ionization energy is like this. 14.5. 14.5. Here second, 29.6, 29.6. NIST used two different ionization energy. Okay, for removing first one, this. For removing second electron, they use this. Okay. But yes. Yes. Be careful, please. This is important. Electrons are not identical particles in a multielectron atom. Each ionization energy represents a different proton-bound electron with different wavelength, and the ionization energies of remaining electrons don't change, don't increase when some of the electrons are removed. First ionization energy removed here. And second ionization energy used, two of that removed, two electrons removed. Okay, by using 29.6, NIST used two of that. First and second, only that. And gain these, gain what? Gain, these are yields, spectral lines, by using these two ionization energies. Okay. Second, first, second, second, second, first, first, first. Ionization energy. So important. Okay. This is so important. Why? When some of the electrons are removed from the multielectron atom, yes, and the ionization energies of remaining electrons don't change, don't increase when some of the electrons are removed from the multielectron atom. Okay. Because there is no attractive or repulsive forces between electrons and protons and between electrons. There is no shielding effect. There is no shielding effect. Each electron with different wavelength connected with only one proton, and they intertwined. Okay. And two, ground state is the highest energy state of an electron in an atom. For each electron. Here, no disturbing the atom. Here, ground state, ground state, ground state, ground state. Okay, and highest energy state, contrary to accepted physics theories, according to me, ground state is the highest energy state of an electron in an atom. In this situation, a proton-bound electron motion form is undisturbed, didn't expand, so it didn't lose its initial energy by the effect of a successive wave from outer side yet. And it has its highest point mass and point energy in this state. 3. A proton-bound electron motion form can expand or shrink under the influence or not influence of successive waves at rate of effective successive wave number squared, like this. This is the formula. Okay. Smaller, greater wave number. And we use here, what we use here, we use 7th electron, we use 6th electron, but in this formula that I put forth, and we gain theoretical result. When we compute, these are results. If you compare, you see observation from NIST data, experimental results and theoretical results that I put forth are the same. Yes, like this. Compare right side NIST data, left side my computations. Okay. Here, then here, I'm sorry, upside down. Yes, it's not important now. Here, important first page for me. Then, finally, eventually, I mean, what? How can I say there are no electric force between electrons and nucleus in an atom? Okay, wait a moment. Absorption process 4. Absorption process is an energy losing process of an expanding proton bound electron motion form. An emission process is an energy regaining process of a shrinking proton bound electron motion forms. While shrinking, a proton bound electron motion form pour out single wave pulse, spectral line. Each spectral line in wavelength terminology represents by single wave pulse. Okay. Five. For instance, if the ionization energies of the remaining electrons changed, this is important. For instance, if the ionization energies of the remaining electron changed when you removed first electron, okay? You removed first electron, okay? Then, from the nitrogen atom, the last and smallest electron should have given a different result. Should have different ionization energy. But look at that. Seventh electron, but in this spectral line, only first electron removed. But I have computed according to my formula. And according to, I have computed this wavelength is 1.85. Okay. When first ionization energy used in experiment, in measuring. Okay. Secondly, if you use second ionization energy to remove spontaneously 2 electrons you remove, then it must be changed its wavelength. Okay, but for each cases, first ionization energy and second ionization energy using, we can use same electron with same wavelength that is represented by same ionization energy. There is nothing changing. There is no change whether you remove first electron and you remove two of electrons. These two last ionization energies are the same. Okay. Removed one. Okay. Removed two, one. Removed two. But they are the same. How we know that? We know that for this case and this case, I use same ionization energy represented same wavelength. So, eventually, therefore, whether we remove whether one electron or two electrons remove